Dear students, so in this module we will learn about the definition why these are named as outer sphere electron transfer reactions. We will learn about no ligand bridging takes place in outer sphere reactions, rather undergoes ordinary electron transfer processes. The outer sphere reactions may involve some metal and ligand or different, both of them can act, metal and ligand. Further, the oxidation state of reacting metal ions must be different. Some metals and ligands undergoing electron transfer are called self-exchange redox reactions. We will discuss it later on. Electron transfer rate is faster than substitution of the ligands. Nevertheless, electron transfer is rate determining step. So, as far as the introduction about the mechanism of redox reactions, especially outer sphere reaction is concerned, the metal complexes which do not go through substitution reaction involve outer sphere electron transfer reactions. It means none of the bonds are broken or formed in either of the metal complex reactants. In other words, these reactions include complementary change in the oxidation state of both the metals through a pathway where the ligand does not undergo bridging mode in the coordination sphere of the complexes. As I discussed in the previous module, that where the direct electron transfer process occurs, none of the other parameters are changed except electron transfer process. Rather, if the coordination sphere of the metal complexes are involved, that involves the transfer of ions, ligands, etc., and that is called inner sphere type of mechanism. So, in this particular module, we are going to talk about the outer sphere reactions. So, therefore, coordination sphere of the metal complex reactants in outer sphere reaction is intact. The favorable factor for an outer sphere reaction is the inertness of the complexes towards substitution over the time needed for the redox reaction to occur. What does it mean? Means the time required for an electron to transfer from the reactant that is going to be oxidized to the reactant which is going to be reduced is much faster than the substitution reaction, and nevertheless this electron transfer process for such reactions is rate determining step. So, the example is like M containing A plus 1 charge having X number of L ligands and another metal ion having B charge over here and Y number of L ligands are now reacting together with and forming M N plus with X number of ligand, means the one charge was reduced, and rather in the reductant, that is M B plus 1 and Y number of L ligands. So, its reaction is written as M A plus 1 plus L X plus M B plus L Y, and it leads to the formation of M N plus L X plus M B plus 1 X L Y. Again repeating, the reaction is straightforward and it is written as M A plus 1 plus L X, X is the number of ligand, that is oxidant, and another reactant is M B plus whatever is charge on the metal ion, and Y is the number of ligands over here, and it is a reductant. When the reaction has taken place, what is formed? M N plus L X, means the number of charges are reduced, and in other complex it is M B plus 1 plus and Y is number of ligand, means the charge is increased. So, it is evident that the electron transfer has taken place from the oxidant to the reductant. The examples of outer sphere reactions are Fe2 plus Cn6, overall charge is 4 minus, reacts with iridium hexachloride where iridium is in plus 4 oxidation state, and it leads to the formation of Fe3 plus hexacyanide and the overall charge is 3 minus, and iridium 3 plus where 6 chlorines are attached, that is IrCl6 and iridium gone to plus 3 oxidation state. So, if you compare, iridium was in +4 oxidation state in the reactant part and iron was in +2 oxidation state. While in the product, the iron has gone to the +3 oxidation state and iridium has gone to +3 oxidation state. So, iridium was reduced and the iron was oxidized. In a similar fashion, another question is that the reaction involves Fe substituted methyl substituted bipyridyl whole thrice 2 positive and another Fe simple unsubstituted bipyridyl thrice 3 plus. So, at one end both are, if you see, both are iron complexes, but one is +2 in oxidation state and another is +3 in oxidation state. So, what happens? Upon electron transfer process via outer sphere mechanism, the ligands attached to the metal center, their coordination number and everything remains same. What is changed? Basically, the species that was in +2 oxidation state has gone to +3 and the one that is +3 in oxidation state has gone to +2. So, the rate of reaction is dependent on the moiety, that is Fe substituted bipyridyl 3 2 positive plus Fe bipyridyl whole thrice 3 positive, means it is dependent upon both the reactants which are undergoing for the electron transfer process. These reactions are genuinely quite fast and therefore Lx or Ly exchange or bridging occurs. Redox process takes place. The coordination sphere of the complex remains intact because the reactants do not interact significantly with each other during the electron transfer process through space diffusion control method. It is a simple scheme that shows oxidant is transferring the electron and the species which is accepting the electron, that is being reduced. The examples of such behavior is self-exchange process between two homonuclear complexes. Homonuclear complexes are where both the metal ions are same, even the ligand molecules are also same. The example representatively written as Ml6 2 plus Ml6 3 plus leads to the formation of Ml6 3 plus and another Ml6 2 plus. For the better representation, we can say Ml6 2 plus M prime L6 3 plus, which goes Ml6 2 plus and M prime L6 3 plus. So, you see nothing has gone changed except the charges noted as a counter cation, means the 2 species +2 species gone to +3 and +3 gone to +2. There are a lot of reactions of self-exchange reactions, you know, that at Fe bipyridyl system attached where Fe is in +3 oxidation state and it is D5 in configuration and it is in low spin case. Another Fe is in +2 oxidation state and it is D6, that is also in the low spin. So, the rate noted for the when both the systems are, you know, one is in D5 configuration and another in D6 configuration. So, the rate goes quite higher, it is more than 10 to the power 6. On the other hand, if you see, the metal is iron and the ligand is H2O. There are 6 H2O ligands attached and now the D5 complex, that is iron 2 plus, is high spin, as well as the D6 complex where the iron is in +2 oxidation state, both are high spin, and for this reaction the rate of reaction is just 3, much slower than that of the bipyridyl substituted iron complexes. The similar fashion, osmium contains tri-bipyridyl system and it is in low spin system for both osmium 2 plus and osmium 3 plus, means D6 and D5, and the rate again goes more than 10 to the power minus 6. If you take cobalt as a metal and 110 phenanthroline as a substituent, so there are 3 110 phenanthroline attached in an octahedral manner. So, what happens? Cobalt 3 plus, that is D6, is low spin, and cobalt 2 plus, that is D7, it's high spin. So, when the cobalt is D6, it is low spin, but when the cobalt is D7, it is high spin and the rate is bit enhanced and it is reported to be 40. On the other hand, when triethylene diamine system tris ethylene diamine system is attached to the cobalt center, and then if it is D6 means cobalt is in +3, it is in low spin, but when cobalt is +2 it is D7 high spin, and the rate is now much slower and it is greater than 10 to the power minus 4. These are the data that by that you can understand what is the role of ligands and the electronic configurations of the metal center that plays significant role in outer sphere type of reactions. The representative example of self-exchange reaction is ruthenium. The ruthenium complex RuNH3(6), that is hexaamino ruthenium in +2 oxidation state, and its ruthenium isotope Ru star NH3(6) 3+. Again I am telling that these systems are basically same, except one ruthenium is in +2 oxidation state and another ruthenium is in +3 oxidation state. When the electron transfer proceeds, forming the RuNH3(6) 3+ and Ru star NH3(6) 2+. So in this case the rate of reaction has been found to be 8.2 into 10 to the power 2 mole inverse second inverse. So what does it mean? It means that the rate of reaction is dependent upon which metal is there and which ligand is attached. So the redox couple Ru and Ru star 3+ 2+ is having the redox potential of reduction and oxidation, that is 0.051 volt, where ruthenium and ruthenium stars are isotope, and for them delta G standard equal to 0. The similar exchange self-exchange reactions are also noted, like cobalt hexamine 2+, cobalt hexamine 3+. When they react together, they form cobalt, that is 2+, complex is converted to 3+, and the one that is 3+ is converted to 2+, and rest of the parameters are same. However, if you note down the rate of reaction for this compound, this complex couple, redox couple, if you see the rate of reaction of this particular system where cobalt is attached with the hexa-ammonia ligands and rest of the story is same, what happens, the rate of reaction is now 10 to the power minus 9 mole inverse second inverse. It is much slower than that of the ruthenium system I just discussed. So despite odd situation and requirements for an outer sphere reaction, the slowest energy barrier is nevertheless can yet be presented by an outer sphere pathway. This criterion ambiguity is observed in metal aqua complexes in which one of these are labile, means there are two complexes redox couple, so one of them could be should be labile, so that it goes for the redox reaction transfer than the substitution. So the substitution reaction for such reactions must be slower than the redox process to occur. The time scale for the redox reaction must be faster than that of the exchange reaction or ligand exchange reaction or substitution, anything. So another reaction noted is chromium star, that is isotopic chromium with hexa aqua complex, that is Cr star H2O(6) 2+, and another chromium hexa aqua complex that is in +3 oxidation state. Now in this case both the centers are chromium and both the ligands are water. A redox reaction has to be observed. You see after electron transfer where chromium isotopic goes to +3 and chromium, that is hexa aqua chromium non-isotopic, that is +2. So the redox reaction has taken place and the rate of reaction has been observed to be 2.5 into 10 to the power minus 5 mole inverse second inverse. So for such a reaction indirect arguments may be arised, because outer sphere rate of reaction for oxidation of hexa aqua chromium 2+ complex appears to be typically 10 to 60 times lower relative to the well known outer sphere reaction involving Cr H2O(6) implying same oxidant. The relative rates of self exchange reactions for chromium hexa water 3+, chromium hexa water 2+ redox couple versus if you talk about the ruthenium penta ammonia single water, that is Ru NH3 whole 5 H2O 3 plus and NH3 whole 5 Ru H2O 2 plus. This couple is fairly informative because the higher oxidation state, that is +3 charge of the complex, is transferred and it is formed by the hydroxo complex. Why hydroxo complex? Because ruthenium aqua group is attached and it can go for the hydroxo formation of the complex. So the maximum rate for self exchange reaction for a specific chromium 3 chromium 2 couple is 2 into 10 to the power minus 5. However, the rate for ruthenium 3 ruthenium 2 redox couple is not directly measured, although it was rationally specific rate for ruthenium 3 ruthenium 2 redox couple can be considered close to that for ruthenium hexaamine 3 plus and ruthenium hexaamine 2 plus redox couple, that is 1 into 10 to the power minus 3 mole inverse second inverse. Now, the mechanism of outer sphere redox reactions. The mechanism of outer sphere reaction initiates with the formation of a precursor complex, which further undergo rearrangement route to become suitable for electron transfer process. In these reactions, one of the reacting species utilizes the second coordination sphere or outer sphere of the reacting species. Both the reactants involved must be inert towards the substitution, as I told that both the systems should be more prone for the electron transfer process rather than the substitution process, and these systems prefer outer sphere mechanism over the inner sphere type of mechanism. So the general mechanism is an oxidant comes with the contact of a reductant and it goes to form a bridge of oxidant and reductant where both the coordination spheres are intact, and now this mixture of oxidant and reductant which are close enough further undergo electron transfer process where oxidant becomes negative in charge and the reductant become positive in charge. So it is written as OX minus and RED reductant positive. Now this oxidant minus and reductant which are close enough now dissociate, and after dissociation it forms oxidant negative plus reductant positive. So overall equation is what? Oxidant plus reductant, there is certain rate of reaction for their combination and forms oxidant combined with reactant, and that is called association. Now this associated complex where the oxidant and reductant are close enough involve electron transfer process, and now it converts to the oxidant minus and reductant plus. Further, this complex, when the electron transfer process is over, then the oxidant, this complex oxidant minus and reductant plus complex is dissociated and forms OX minus and reductant plus. So in the complex form, it can be depicted as, first, precursor complex formation is basically that where both the reactants weakly interacting to each other without changing their oxidation state and they are in equilibrium, means Ma plus 1 plus Lx plus Mb plus Ly, equilibrium constant goes to Ma plus 1 plus Lx weakly interacting with the Mb plus Ly, that is called a formation of precursor complex. In the second step, the reorganization of the precursor complex takes place. And why this reorganization takes place? To make this precursor complex suitable for the electron transfer process, so that the electron transfer can be facilitated, and when the electron transfer is facilitated, it relaxed to the successor complex. So what happens? The precursor complex further undergoes electron transfer where Ma plus 1 plus goes to Ma plus and Mb plus goes to Mb plus 1 plus, and that is called successor complex. In the third step, the dissociation of successor complex eventually leads to the formation of ultimated product where both the complexes have changed their oxidation state by 1. So that is called a dissociation step where Ma plus 1 plus Lx interacts with B plus Ly and dissociation goes Ma plus Lx plus Mb plus 1 plus Ly. So, the rate of reaction can be determined from step 2. Step 2 is what? That is electron transfer process, which is the slowest step for the reaction. Whereas the formation of precursor complex as well as dissociation of the successor complex is quite fast. Therefore, the thermodynamic energy profile diagram for outer sphere kind of reaction is like that: reactant, which are minimum in energy, then it goes to the higher energy, and then it forms a precursor complex, so it comes down. The energy is minimized. Then again there is a transition state formation where the electron transfer process takes place. Now they adjust their bond lengths like that. Transition state, the electron has equal probability in the transition state to be either of metal, means it could be on one reactant and is at equal probability to go to the another reactant. So when such a scenario is created, the energy of this system is raised, and it is the most unstable stage of the associated complex. Rather, it again forms a successor complex and after electron transfer process, and as soon as the electron transfer process has occurred, the energy goes down, and when energy goes down, it leads to the formation of a successor complex. So how the plot goes? Reactant, then transition state, precursor complex, then again it goes to the transition state most high in energy, where electron has equal probability to be in either of the metal complex, and then the electron transfer takes place and at this unstable stage, and it comes down and forms a successor complex. This way, and now the complex is successor complex is dissociated to form products. So this is the energy profile diagram, how the energy states of the various stages change, and ultimately the outer sphere process is over. The change in free energy is what? It is equal to delta G, that is energy required to bring the reactants together with, plus delta G0, that is the energy required for a solvent recombination, plus delta Gi, that is energy needed for the change of bond lengths by bringing orbital in the same energy level. What does it mean? Total energy change is contributed by three kind of energy changes. First, when both the reactants come together, that requires an energy. So this energy contribution, plus if you are doing some kind of experiment in particular solvent, the molecule needs to be oriented so that it can be well suited for the electron transfer process, and therefore the complex has to be reorganized, and this way solvent recombination reorganization takes place, and that requires an energy. So this is the second type of energy, and the third is energy needed to change the bond lengths, because to become equal probability for the electron to be in any of the metal, the transition state, that is the most unstable energy states, where all the bonds are adjusted so that the electron transfer process can occur. So these three parameters contribute the total change in energy of the products than that of the reactants. So in summary, the outer sphere reactions can be homometallic or heterometallic in nature, but whenever these are homometallic, these are named as self-exchange kind of reactions, like iron 2 complex, iron 2 aqua complex, or iron 3 aqua complex, iron 2 phenanthrolene complex, iron 3 phenanthrolene complex, and in both the cases the metal center is same and the ligands are also most likely to be same. Second, the outer sphere reaction involve simple electron transfer without sharing or bridging of any ligand. Third, self-exchange reactions imparting metal complexes having same metal and ligands have been illustrated. Fourth, the redox reaction rate must be more rapid relative to the substitution of the ligand. This is a very important point, where the redox reaction must be faster than the substitution of the complexes. Next is the Electron transfer process is the slowest path due to the electrostatic repulsion, and thus it is rate determining step. And the last, eventually electron transfer occurs if all the orbitals of the both the redox couple are same in energy. It means all the parameters for both the reactants, oxidant and reductant, should be unique so that it facilitates the electron transfer.